McGrath, and I work for the Cortland County Soil and Water Conservation District. The district works with all kinds of landowners and municipalities to protect our soil and water resources in Cortland County. I'm called a water quality specialist, so I work with all kinds of water in Cortland County. I work with streams and rivers, I work with lakes, I work with stormwater, which is the water that runs off the land during a rainfall event, and I work with groundwater. I work with municipalities to help them protect the groundwater. Groundwater is really important because it's the drinking water supply for much of Cortland County. And groundwater is connected to surface water. So what we do up here on the surface of the earth can affect the quality of our groundwater, which means it can affect the quality of our drinking water as well. This video is going to talk about what groundwater is and where it is, and why it's so important to protect it. And we're going to talk about the different things that can contaminate the groundwater, and then how we know if it's clean. Today I want to introduce someone special. His name is Wethje, and he's the water supervisor for the City of Cortland. He's in charge of protecting our drinking water supply and making sure it's clean.
Hi, I'm Wethje, Chief Water System Operator for the City of Cortland Waterworks. We provide drinking water to the City of Cortland. We get that water from an aquifer. We refer to it as the Cortland Homework Prevalent Aquifer, and it is a sole source aquifer. That is a designation given by the Environmental Protection Agency, which means it is the only source of drinking water for the City of Cortland. That destination is important because it provides protection from the potential for contamination by development over the aquifer. We have 3 groundwater production wells. They range from 55 to 77 feet deep. Our main production well is 77 feet deep, and that will yield 3 million gallons per day for an average daily demand of 2.5 million gallons. Groundwater may have harmful bacteria present, so we disinfect the water before sending it into our distribution system. We disinfect with chlorination. We have a combination of liquid chlorine, or sodium hypochlorite, and calcium hypochlorite, which is solid chlorine. Let's take a look at that process now. Here we have containers of sodium hypochlorite. We use a chemical feed pump to inject the sodium hypochlorite into a 24-inch water main. From here, the water goes to a 3 million gallon storage tank. That storage tank provides drinking water storage, and it also provides pressure to our water system due to its elevation. After the water enters the storage tank, it goes into the distribution system, where it serves over 70 miles of water mains, over 500 fire hydrants, for a population of 19,000.
So now you know a little bit about groundwater, but maybe it still seems like a bit of a mystery. So I have some pictures here that hopefully will help you explain and understand groundwater and how it works. So what is groundwater anyway? So groundwater, here we have a picture. It's got, if you imagine a slice through the earth vertically, where up at the top we have grass and trees, and this is where we live and conduct our own activities. Below that is a zone called the unsaturated zone, and that means that it's rocks and dirt, but the air spaces between those particles is full of air. Below that is called the saturated zone, and it's like the upper zone, except that it's saturated, meaning that the pores or spaces between rocks and gravel is filled with water instead of being filled with air. The line between the two, between the unsaturated and saturated zones, is called the water table. This is a really important line because it shows us essentially how deep we need to sink our wells to make sure that we hit water. How far down is the water? Well, it's below the water table. And the water table also tends to be related and correlated with surface water, the surface of a lake or the surface of a river that's moving very slowly and is essentially slack water or flat water. And so this is a bit of terminology about groundwater. So groundwater fills the spaces between soil particles and fractured rock beneath the Earth's surface. This is the hydrologic cycle. It's the cycle of where our water is on the Earth and all the different places it goes and how those places relate. So it starts off with precipitation, which is either rain or snow that falls on the surface of the land. From there, it can go various different places within the hydrologic cycle. In some cases, it runs off and gets directly into our streams or rivers, so into a river or ultimately into the ocean. It can land on the leaves of plants and trees, and it can be taken up by those trees. Those trees then release water as part of their natural cycle, and that's called transpiration. The other thing it can do directly is evaporate, which means it lands on any kind of surface, a roof or a tree or a sidewalk. The sun heats it up and it goes back into a gas phase and goes directly back up into the clouds immediately. So those are some places or some ways that it doesn't really sink in or do anything. It gets sent right back up. It's called evapotranspiration as a combined term back into the clouds. But if it sinks into the soil, then it ultimately joins groundwater. And that is where we get our water from. It percolates down in below the water table into groundwater. It may feed a river or a lake and add water to that water body, or it may not. And it can also ultimately feed a large river like the Chiafnioka River north of Cortland, or make it all the way to the ocean and feed the ocean water through an underground pathway. All the ways that it goes back up into the clouds then closes the cycle and puts moisture back up into the clouds and available again as precipitation. So that's the hydrologic cycle. The water that gets into the groundwater is where we take our water from. And we've used the word aquifer before, but what is an aquifer? It's a body of permeable rock which can contain or transmit groundwater. So there's water in the rocks, and it has to be able to move because the water that's replenished through rainwater, groundwater is always moving. Some people call it an underground river. It really isn't quite like that, but it does move very slowly downhill. In our case, from up at Gracie Road area in Cortlandville to the south, it moves very slowly north towards the Chiafnia River north of Cortland. That's kind of the direction of flow. It's very, very slow, but it is discharging slowly into the river, and it's being replenished at all the places by rainwater that trickles in. And so this is a picture of the infrastructure that we use to get water to our homes and businesses. We've talked about wells, and if you don't really know what a well is, what it is really just is a big tube that's been drilled into the ground to hold a space open for water to come into that tube. It's a closed tube through the unsaturated zone, and then a portion of the well or the pipe down in the saturated zone is screened, which means that water is allowed to get into the pipe, but very fine sediments are not. And then a pump then pumps that water up usually into a kind of a reservoir that makes water available to us even when we have the pumps taken offline or something like that. We have a storage body of water that's available to us. Now, in a home system, there might be a very, very small pump. It could even be in a small well directly up into the home. But a very large system like a municipal water supply will have one or more very large wells with very large pumps like you see here, pumping into a very large reservoir because it's serving a lot of people. And then there will be these pipelines underground that will then deliver water to each individual house. And we've mentioned, I think, that surface water and groundwater interrelate. They're not separate systems. Rainwater can hit the surface of the land. It can drain to a river. And in some cases, in this case, it can drain to a river, and then in a losing section of stream, the water in the river actually contributes water to groundwater. And that's when the water table is low. It depends on, say, late summer, early fall, when there hasn't been much rain. The water table will be low because there hasn't been much replenishment. And it also depends a little bit about where on the landscape you are. If you're down in a big river valley, the groundwater will be more like this situation where the groundwater is giving water to the stream for the most part. But the point is that they interact. They can interact in different ways and different locations, but groundwater and surface water are not independent systems. They're all part of the hydrologic cycle, and they interact directly depending where on the landscape you are. We've looked at some pictures of groundwater and how it works, but sometimes it's helpful to look at what's called a model, which can show us and help us see how groundwater works. This is a groundwater model. It looks a bit like an ant farm, but we're going to look at water instead of ants with this. So if you imagine a slice into the earth where up here, this is a little picture of people for scale. This is the surface of the earth. This might be a 6-foot tall man, and which means that the slice through the earth is quite deep, and that's how deep our aquifer is. It's about 100 feet deep. So they're up at the surface. And then some of the features that are important in groundwater are things like drinking water wells. These are wells going down into the earth. Some are shallower, some are deeper. And a stream cuts down into the ground as well. And then where the water level is in here affects whether the wells have water, for example, or whether the stream is dry or wet. So we're going to zoom in on the model, and then we're going to use it to actually make groundwater sort of come alive for us and show us how groundwater and surface water works and interrelate, and also how the activities that we do on top of or on the surface of the earth can affect both our drinking water quality in the wells and also the quality of the water in a stream. Now we've zoomed in on the groundwater model. In the ground, there are two different zones. One is called the saturated zone and one is called the unsaturated zone. The saturated zone is down deep where the pores, they're called, or spaces between the rocks and gravel, are full of water. And above into the unsaturated zone, those spaces are full of air. And the line between the two is called the water table. If you can see it here, the water table over here, it's right here if you can see the reflection. And that water table is also reflected in these wells. These are wells. One of them is shallower and one of them is deeper into the earth. You can also tell this stream is dry, which means the water table is below the bottom of the stream. And the water table is usually about the same all the way across. So this is the unsaturated zone and this is the saturated zone. The water table is in between. Now under this might be conditions, say in late summer or during a really late dry and late summer and fall, where the water table is quite low. The groundwater, we're threatening this well, it doesn't have much water in it, so a house drawing from this well might even run out of water. These deeper wells are okay because the water table is higher than that, so there's still lots of water there. But what if it rained? What if it rained and the water ran off the ground, off the earth, and into this little stream, and we gave the stream a lot of water from rain, a good-sized rain. So now the channel has rain in it, water in it, and if you look at what happens to the water, if you can see the line slowly dropping, but what it's doing is it's contributing water to the groundwater. And so the water table is rising, the stream is still falling, but there might be a balance at some point where, again, they reach the same point, and maybe the stream will even hold water. The other thing we can simulate if we let all the water out of the stream and let it settle a little bit. The other thing we can do is make it rain on the surface of the water, or the land, and show what happens to a stream that's dry. And so this would be a headwater stream that's dry a lot of the time, and we get a big rain across the whole earth. Oh, I forgot to point out, here's our little people again for scale. So that's maybe a 6-foot man and a girl. So this is very deep into the earth. It might be 100 feet into the earth. And just remember that this slice of the earth is quite deep. This is just a model, and a model is sort of a mini version of the real thing. But it can really help you to understand and see how things work. So now we're going to have a big rain where these people live. It's going to be kind of rainy weather for a minute. And we're going to give lots of rain. Lots and lots of rain, and we'll see what happens to the stream. Now all of a sudden, instead of the stream giving water to the ground is giving water to the stream. Okay, so there's a lot of interaction between groundwater and surface water. And there's interaction between the surface where the people are and both our drinking water where these wells are and our stream. So what we do is really important, both the water that goes into a stream but also the water that we discharge onto the ground, say runoff from parking lots or maybe an industry that's spilling something that it shouldn't be spilling, and it falls on the ground and sinks into the ground. That can be really important for our drinking water if it's allowed to sink in and then go down into groundwater. We can end up with contaminated wells or contaminated streams, and we'll show that in just a minute. Okay, now we're going to see what happens if we don't take care of our activities on the surface of the earth and something is allowed to spill or leak. It could happen sort of in a drip, drip, drip way over many, many years, or it could happen in one big spill or one big release, say a catastrophe of a tanker truck spilling or a lagoon of waste or something like that breaking open. So what happens if we release something nasty on the surface? Where does it go and what happens?
We want
now that I'm back at my desk.
So there you can see something nasty sinking into the ground. And then maybe it was a spill and it stopped, and but it's still, years go by and more rain happens. You see our stream now? It's gotten into our stream. Remember, streams can gain water from groundwater, so now it's into our stream. And it's slowly making its way down toward those wells. And so that's how our drinking water can get contaminated and sometimes even ruined. Sometimes we have to find a new water source. The problem with our aquifer, the challenge with it, is that there is no other water source. There's nowhere else that we can get water from. So we have to take really good care of our aquifer. But you can see it getting pretty close to these shallow wells. Our stream is not looking nice at all. And what happens if a contaminant reaches this well and we don't have another source? What happens if our public drinking water supplies are at this elevation? Usually they're pretty deep, but over time they could reach our public water supplies. And this did happen with a spill of a chemical called trichloroethylene back in the late 1980s. It happened up in Cortlandville, but it's been moving towards the City of Cortland wells ever since, and it's still in the water, and it's moving toward the wells. But fortunately, as you can kind of see what happened here, even though it came in a narrow area, it does kind of spread and in that way get diluted. And so that's what's happening with this chemical, is the concentrations or the amount per unit water are actually decreasing over time. So even though it's moving toward the drinking water wells, the concentrations are actually decreasing, not increasing, and that's really good news for our drinking water supply. But what happens if something happened right, and that happened quite a ways upstream from, or up gradient from the wells? What happened if the spill occurred right near the drinking water wells? Then it could reach the wells before there was any dilution or before we even knew that it had happened. So that's an example of why it's really important to protect our groundwater, because it's also our drinking water and because it can also influence our stream quality, water quality as well. We've talked about groundwater already and where it is and what it is, but if you're having trouble imagining that the ground can be full of a lot of water, we're going to use this demonstration to show you that it really can. Here we have 3 jars, one with medium-sized gravel, one with very small gravel called pea gravel, and one with a very coarse sand, the one on the right. And we have equal volumes of water. I've put a little blue food coloring in each one so you can see the water better, and it's the same volume in each cup. So we're going to pour the cups into the jars and see if any of the water will go in there. I'm going to start with the one on the right in the sand, because I know already that the sand will take water, but very slowly. So we're going to give that one a start, and then we'll do the other 2, and then we'll keep kind of working until they've decided that they're all full and we can see that there's water at the top. So here we go. We're going to pour water into each one and see how much they take. So now we've poured a full cup of water into the 2 on the left, and the volume looks to be about the same on the 2 jars to the left, and there's a little water left over in the smaller gravel. We'll keep working on the sand. Let's check in on the sand and see how it's doing. So if the volumes at the top are all the same, that means they're completely full of water, and you can see by what's left over that the one with the larger sized gravel took the most water. The medium sized gravel took almost the same water, but there's a little left over. And then the sand, surprisingly, actually took a lot of water as well, even though it's very, very full of small particles of sand. But there's a little bit more water left over. So now you can see that a full cup of water went into even a full jar of sand, and that even more water went into the gravel. Our aquifer is more like the one on the left, with fairly coarse gravel, although it does have some finer gravel and sand mixed into it as well. And if you can imagine an area that's the size of all the way from Cortlandville up by Gracie Road, all the way down to the City of Cortland by where the Teofnee-Oga River comes through, and imagine it 100 feet deep and as wide as the valley is all the way down, I think you could maybe now imagine how much water is down there. Plus, it's not a finite amount of water. As the water discharges into the river, it flows from the south to the north, and as it discharges into the river underground, rainwater, each time we get rain settles into the ground and eventually makes its way back down into groundwater to replenish our aquifer resource. So now I think you know quite a bit about groundwater from our different trips to the waterworks in Cortland and the pictures that I showed earlier, plus our demonstrations. We've talked about how our activities up on the surface of the land can contaminate both surface water and groundwater, and how much of a problem that would be because we could contaminate our own drinking water supply. This picture just shows some of the sources where contaminants could come from. They include urban runoff and cars. Both of those can contaminate heavy. Cars are a source of heavy metals. Metals are very toxic to humans and other animals. It comes out of the exhaust. It falls on the ground, and then stormwater washes it into our streams or down into the land, into the earth, into groundwater. Industry can produce contaminants both through the air and the water, and the air can then settle via rain onto the earth and get into our streams and groundwater. And landfills, both past landfills that could have included really nasty stuff, hazardous waste dumps, and unregulated landfills, as well as current modern landfills like the Cortland County landfill that's well regulated and protects the water underneath it and the surface water. But both could potentially be sources of contaminants. And we might not even think about it, but our farms could be sources of contaminants. Farms use pesticides and fertilizers, and they store manure. All of these are contaminants that need to stay on the land and not get into our waters. Now, farms, of course, are a really important activity in Cortland County. We have a lot of farms, and that's all okay. It just means that we need to use best management practices to make sure that these potential contaminants stay where they belong and don't get into our water systems. And another example is gas stations. We all have cars, so we all need gas. But gas stations, if you think about it, store quite a bit of gasoline and other products. And if the storage tanks were to fail, or there to be some kind of leak, that could easily contaminate our groundwater. So gas stations can be a source of concern, especially over an aquifer like ours. And sitting in the middle of all that is our water supply. Here's our well down into groundwater, pumping up water. But what if any of these sources are producing contaminants that get down into our groundwater and get into the well where our drinking water is coming from? So that's why it's so important to think about the activities that we do on the surface of the land and how they can move and get into groundwater and hurt us through drinking water, but also hurt the other animals that we share the earth with.
So how do we know our drinking water is safe? Public water systems are regulated by various government agencies, including the New York State Department of Health. They require public water systems to collect water samples to test for a wide variety of contaminants. We collect water samples at our groundwater production wells at the waterworks, and we also collect water samples using monitoring wells.
So now we're out on the waterworks, which the city property where the drinking water wells are, but this is sort of the back of the waterworks, where there's a network of roads that connect to monitoring wells such as this. They provide access to about 12 monitoring wells on the property. These wells provide kind of an early warning system. If something were in groundwater and moving toward the city drinking water wells, monitoring these wells, sampling these wells, would help us know that something was coming so that we could take action, so that the city could take action to protect the water supply. So the Soil and Water Conservation District works with the city monitoring these wells. We do it specifically for a contaminant called trichloroethylene that is in the groundwater from a past spill from the late 1980s. It is moving towards the city wells and has been since then. But the good news is through our monitoring and through the treatment by the responsible party, the concentrations are actually decreasing. So that's great news. So what do we do with a monitoring well, and how do we use monitoring wells? How do we sample them? The first thing we have to do is a monitoring well is a hole in the ground and water collects in it. And the water that's in it is kind of stale. It doesn't really represent the quality of the water in the aquifer as a whole. So the first thing we do usually is take a pump and we put it down the well and we pump out a lot of water. so that we make sure we're getting fresh water from the aquifer drawn in right now into the well, and we're getting a good quality sample. So we use a pump usually to do that, and we throw the water away into a bucket so we know how much water's been removed, because by best management practices we have to remove a certain amount of water, and so we just use a bucket to measure how much we've taken out. When we actually want to collect a sample, we use a baler. This is called a baler, which is a big stainless steel pipe. It has a small hole at the bottom and a little ball that's inside the baler. When you lower it down, and I'm going to do it, we'll show you. And we put a blue tarp here because we don't want to introduce any contaminants into a monitoring well, because that could be adding contaminants to the groundwater, which could end up in the city well. So we have to be careful, because there's animal droppings in the woods and there's things on the bottom of our boots. We have to make sure to not introduce any contaminants into the well. And then we use a stainless steel baler because we don't want to introduce any contaminants to our sample. The sample needs to be representative and not have any foreign materials in it. So we lower this down into the well, and so we hit water. And in this case, water is not very far down. If you look behind me, that bright green back there is Otter Creek. When a creek is very near a monitoring well, it means the water table, the line between where above it the pore spaces in the soil are full of air, below it they're full of water. When you're near a creek, typically the well it's not very far down to get to water. So we don't have to go very far down with our baler to get water. We would pull the sample out, and then this water inside the baler we would use for our sample. So normally I would put it into something like a stainless steel pitcher, and then I could pour that water into sample bottles, and then the sample bottles would go to a laboratory for analysis. And there's lots, if you see here, there's lots of different kinds of bottles. Each different chemical that we analyze for, they have to be preserved in different ways. And say, in this case, this bottle is used for a substance that's sensitive to sunlight, where it would break down in sunlight. And that's why we use the amber, the brown bottle, because that keeps sunlight from getting into the bottle. We can also use, this is called a sonde, a multimeter sonde, that will take measurements for things like pH and conductivity and temperature. And we would use that on the sample as well. And then we would also record some information on the data sheet about the time of day and who was here and the procedures we used, and information like that that would go with the analytical results from the laboratory. So the city and the Soil and Water Conservation District work cooperatively on these kind of monitoring efforts to make sure that the aquifer as a whole is healthy and safe. There's about 12 wells, as I said, on the waterworks, and then there's probably another 30 out throughout Cortlandville that can collectively be used to find out, make sure that the aquifer water quality is safe, and to detect anything if something were to get into the water supply, into the aquifer, we would know it. And so we sample periodically. We do a sort of a check of the aquifer to make sure that the aquifer is still clean and there's nothing that's gotten into it. So this concludes our video about groundwater. You've met Matt Wethje, who runs the City of Cortland Waterworks, and seen how he makes sure that the drinking water for the City of Cortland is clean. You've seen some models of groundwater that hopefully have helped explain how it works, why there's so much water down there, even if it seems odd that there's water in the ground, in dirt. And hopefully you understand a bit more about the hydrologic cycle and where groundwater fits in the hydrologic cycle, the relationships between groundwater and surface water, like Otter Creek behind me. We've talked a bit about different contaminants that can affect groundwater and harm our water supply. And we've also talked a bit about how we know when water is clean, when our drinking water is clean. We've talked about how the city monitors its drinking water supply, and how we cooperatively, the city and the Conservation District, work cooperatively, and the town of Cortlandville, to monitor the aquifer as a whole, to make sure that nothing is coming at the public water supply wells, and that if there is something, a contaminant in the groundwater, that we know it and can take action to stop it from reaching public wells. So you know a lot about groundwater. We hope that you will help us to value groundwater and drinking water and protect our environment.